In these kind of problems, it's very common for a chemist who wishes to make a precipitate of an ion, all right? If you make a precipitate, you can filter the solution with a piece of filter paper, and the solids will be extracted from the liquid, and you can remove them. And if they're dangerous, for example, that can be kind of important. So if you have, for example, in this problem, mercury, maybe you want to get rid of the mercury, which is probably not a bad idea. So let's say that somewhere, maybe in your grandfather's basement or whatever, you find a 0.010 molar mercury 2,2 plus solution. Now, why that was in your grandfather's basement, no clue at all, but just go with it, okay? Anyway, let's say we want to get rid of the mercury. We want to remove the mercury from the water. Well, we can use the fact that this mercury 2,2 plus ion is quite insoluble in the presence of chloride, and it makes the wild Hg2Cl2 solid there pretty readily. The KSP is very small, 1.1 times 10 to the minus 18th, so we know it's very reactant favored. And so if we add just like a little bit of chloride, it should be able to make a precipitate of this weird Hg2Cl2. And again, once you have the solid, you can use filter paper to filter it out, and we can get rid of this nasty mercury. So what we'd like to know in this first part, how much chloride can we add in solution without forming Hg2Cl2? Like, what is the threshold chloride amount that's needed to just begin precipitation of this solid? So we want to know if we need to have like kilograms, or can we add micrograms? That's the kind of question that this kind of thing would answer. It's not too hard to figure out. So we're going to use the fact that the KSP 1.1 times 10 to the minus 18th equals the mercury ion concentration times the chloride ion concentration squared. And our mercury concentration is apparently 0.010. So if you put that 0.010 up for the mercury, you're going to solve for chloride ion. We'll take the square root to get rid of the chloride squared thing. Chloride's going to be the square root of KSP over our mercury concentration. So putting this all together, the KSP 1.1 times 10 to the minus 18th divided by the mercury concentration, which is 0.010. And to find just the chloride, we'll take the square root of it, since there's 2 chlorides per Hg2Cl2. This comes out to be 1.0 times 10 to the minus 8th molar. And that is very, very small. And what that tells you is that it's not going to take a lot of chloride to make a Hg2Cl2 begin to precipitate. And that's kind of cool. Now, chloride isn't usually a very hard ion to come across. It's available, of course, in table salt, NaCl. You can use it in hydrochloric acid. That would be a source of chloride. Lots and lots of sources of chloride. And this number says it certainly isn't going to take very much. 10 to the minus 8th is really small. It's not going to take very much chloride to make that begin to precipitate. So we've decided we're going to go for it. We're going to raise the chloride level now to 1.0 moles per liter. And again, initially the mercury concentration 0.010. So we want to know how much mercury is going to be left in solution when the chloride has been raised to 1.0 moles per liter. And again, chloride is so cheap in terms of NaCl, hydrochloric acid, whatever, it shouldn't be too hard to do this. How much mercury is left? And that's a totally fair question. Well, it's back to the KSP expression for us. In this case, KSP equals mercury times chloride squared, but we want to solve for mercury. We want to know how much is left. So the mercury is going to be the KSP divided by the chloride ion squared. Well, KSP is still 1.1 times 10 to the minus 18th. Divided that by the chloride concentration, which is 1.0 and 1.0 squared. And lo and behold, the mercury is now 1.1 times 10 to the minus 18 moles per liter. That is small. Now, chemists will like to collectively pat themselves on the back because you started with a roughly 10 to the minus 2 molar mercury, and we went to a 10 to the minus 18 molar mercury. So that's about 16 orders of magnitude that it's dropped, and that is considerable. That's a lot of mercury being lost. So in this case, we have gotten rid of a lot of the mercury. But you'll notice I didn't say all of the mercury. You do still have 10 to the minus 18th moles per liter. Now that's hardly a lot. It doesn't seem like it would be very much, but maybe your system is really sensitive to mercury. So just realize we'll talk here about separating metal ions and stuff like that, but it's not a complete separation. There's always going to be a few atoms running around. So even though we went to orders of magnitude smaller, it's not a complete separation. Keep that in the back of your mind, especially if you have a really sensitive reaction. But at the end of the day, I would pat myself on the back because an order change of 10 to the 16th, that's huge, all right? That's a huge, huge amount. So yeah, pretty cool. However, if you're really sensitive to mercury, whatever system you're looking at, maybe 10 to the minus 18th is still too big, and you might have to add another chemical to make that value of the mercury 2,2 plus go down even more. So just think about that in the back of your mind. So here's a reaction with strontium carbonate, and we want to know the concentration of carbonate required to begin precipitation of insoluble strontium carbonate from a solution containing 0.050 molar strontium 2 plus ions. Okay, so here's the big picture. We must have found now in my other grandfather's basement, if you will, a 0.050 molar strontium solution. And again, why they'd have a strontium solution, I don't know. However, we realize that strontium carbonate has a small KSP, 5.6 times 10 to the minus 10th. So if we start adding carbonate in, we can begin the precipitation of strontium carbonate. We can filter out then the solid and lower the strontium concentration down. Well, anyway, in this problem, we'll use the fact that KSP equals strontium times carbonate, the strontium ion times the carbonate ion. And we have there the concentration of the strontium ion. We just want to essentially solve for carbonate. So what this looks like, KSP equals strontium times carbonate. Carbonate is what we want to solve for. Carbonate is going to equal KSP divided by the strontium ion concentration. And it comes out to be 1.1 times 10 to the minus 8th moles per liter. So again, a very small amount of carbonate will be needed to begin precipitation of strontium carbonate. And if we push that carbonate level a little higher, we'll start to lower that strontium level quite considerably.